Hello everyone, welcome to my channel. Myself Mansa and currently pursuing my engineering in Sri Venkateshwara College of Engineering. SEM 3rd SEM Bhaskara section. Subject Digital Design and Computer Organization. Topic Sequential and Combinational Circuit. Introduction. The problem tackled in this paper is that while sequential synthesis techniques such as retiming and combinational optimization improve circuit performance, verifying the equivalence of these sequential circuits after optimization remains difficult. Traditional methods for sequential verifications are impractical because of the complexity introduced by latch movements, especially in the circuits with feedback loops. The authors propose a solution that reduces the complexity of the sequential verification by transferring it into a combinational verification problem. For a certain class of circuit, this transformation is achieved by imposing constraints on latch feedback paths, allowing the use of existing combinational verification techniques or more efficient process. Retiming and combinational optimization. Retiming is a powerful optimization technique used in sequential circuit that involves moving latches to improve timing and performance. However, retiming alters the circuit structure, making sequential verification more challenging, as it disrupts the one-to-one correspondence of latches between the original and transformed circuits. Current simulation-based methods are insufficient for circuits that have undergone such transformation. For circuits that have undergone such transformation. To address these issues, the authors are focused on reducing sequential verification problem to a simpler combinational verification problem by leveraging combinational optimization techniques. These techniques allow for improved circuit design without the need of complex state space explorations typically required in sequential verification. Steady state equivalence. The verification technique presented in the paper relies on the concept of steady state equivalence. Unlike typical methods that assume a power of initial state for the latches, this approach assumes that each latch starts in an intermediate state. The circuit is considered to have reached a steady state when, for a given sequence of inputs, all the outputs become determinate Boolean values. Steady state equivalence between same values for all the valid input sequences once they each reach the steady state. This approach allows the authors to focus on comparing circuits based on their stable behaviors rather than exploring the full complexity of their initialization states. Circuits with feedbacks. For sequential circuits with feedback paths, the situation is more complex. The feedback in these circuits creates cycles which need to be carefully managed during the verification process. The authors propose modeling a feedback latch as an enabled latch with separate data and enabling signals, allowing the feedback path to be transformed into a combinational representation. However, this representation is only possible for latches those whose next state functions are positive unit, meaning they are monotonic with respect to the latch variable. For circuits that do not meet their conditions, the paper suggests exposing latches, treating their outputs as the primary inputs to break feedback cycles, thus allowing verification process or to proceed. Experimental results. The paper presents results from experiment conducted on various benchmark and industrial circuits. The results demonstrate that proposed method of combining retiming and with the combination optimization yields significant improvements in circuit performance, including reductions in circuit delay and array in case where circuits underwent retiming and combinational synthesis. The delay was reduced up to 50% compared to the circuit optimized using purely combinational methods. The verification process was also found to be efficient, with the most circuits being verified under a minute. The experimental result validate the effectiveness of the approach in handling both small benchmark circuits and large industrial design. Conclusions and future directions. The paper concludes by summarizing the key contributes of the proposed verification techniques, which reduce the complexity of the sequential verification by transforming it into the combinational verification problems. This approach allows for efficient verifications of circuits that have undergone retiming and combination optimization. The authors acknowledge that while the method works for a large class of circuits, further work is needed to extend the technique to handle circuits with enabled latches and more complex feedback paths. For future research will focus on developing more complete methods for distinguishing between events and signals, as well as improving the optimization and verification of the industrial scale circuits. Thank you. Please like, share and subscribe to my channel.